Hello and welcome, class. We are going to be picking up in Chapter 4, following from our conversation of electron configurations. We are now going to be taking those electron configurations and actually doing something with them. We are going to be using them to explain the following: group properties and periodic trends. So now we are taking those electron configurations and using them to understand the actual behavior of atoms. Notice in the page number description, I'm sorry, it's too much. I tried to condense as much as I could, I promise. We have a throwback to Chapter 2, but the organization of Chapter 4, man, I have no explanation for it. All of the group properties and periodic trends, which fit so nicely together in our conversation, if you're reading through in the text, are just kind of all over the place. And for that, I apologize. Sadly, there's nothing I can do about it. Again, I wanted to condense. I tried as much as I could. But this is the spread of the page numbers that corresponds to what we are going to be talking about. All right, so let's just jump into it. All right, so the periodic table we have already used as a roadmap. We've used as a powerful quantitative tool. It didn't just appear out of the ether, though, and it hasn't always looked the way that we are used to it looking. DIMITRI I pronounce his last name MENDELEEV. I've also heard it MENDELEEV. Either way works. Was a chemist, physicist, natural philosopher who was alive from the years 1834 to 1907. And what he is attributed with is writing, organizing the first periodic table. It's not necessarily that his periodic table was the first published or the first that ever existed, but his periodic table was the foundation for the periodic table that we use today. So it's like the grandfather of our current periodic table. Dmitri Mendeleev recognized that when certain elements were arranged in order of their increasing relative mass, certain sets of properties were found to reoccur periodically. So that's where the periodic table gets its name, is because the certain properties of elements on the table repeat. They are periodic. So his periodic table we can see down below. It looks very different than the one that we use today, but not as different as one might expect. What he found as the work in the day, just to give a little bit of context for what he was doing, he was working in a time when the masses of certain elements were just being discovered. So this was all new information, relatively new. And he found that if you were to observe elements like hydrogen, lithium, sodium, potassium, rubidium, cesium, etc., these are elements that all reacted in a particular way when in the presence of water. Each of these could, when added to water, pretty readily react and form a positive ion in solution. And as you worked your way down his periodic table, the reactive vigor increased. And this was true of a lot of the elements that we could see on his periodic table, some of which are organized in the same types of columns or across the same rows as we see nowadays. For instance, on our modern periodic table, the top of the P block is B, C, N, O, F. And on his periodic table, we can see that they are arranged in the exact same way because they go from low to high relative mass. In addition, if we observe boron on our modern periodic table and look directly below it, we see aluminum. If we look on our periodic table and see carbon and silicon, the same thing is occurring here. So his periodic table in terms of trend matches a lot of what we still have today. Again, our blocks look very different, but the same types of trends can be seen even in his periodic table. Something else that was super awesome about his periodic table is that it had real predictive power. I mean, there are some slots on the periodic table that we can see here that are blank. He predicted, based off of the reoccurring trends and the relative increases of masses that were observed on his table, that there would be an element that had a certain mass that is equal to 68 atomic mass units. He predicted that there would be an element that had an atomic mass of 72 atomic mass units. He predicted that the reason why the elements were not listed on the table yet is because they hadn't been found. He predicted that these would be elements that we would still need to discover. Maybe they're just too reactive, maybe they're too hard to isolate from an ore. Whatever the situation was, they should exist, we just hadn't found them yet. And it turned out that he was right. So the element with the atomic mass of approximately 68, we can look on our periodic table. As we can see here, as we're tracing our way back, it would appear as though the element gallium has a mass that's pretty close to 68. I mean, it's 69.7, but it is the only element on the periodic table that has this mass, and it was not present on Dmitri Mendeleev's periodic table. Similarly, the one that he predicted that would have an atomic mass of 72, we can see right here is germanium, also which was not present on his periodic table. We have since discovered these elements, now have characterized them, we've isolated them in like relative abundance, we understand what their properties are. And so here we can see a more modern construction of our current periodic table. Will this someday change? Maybe. It's the most conventionally used, but there are plenty of alternate periodic tables out there that have the elements arranged in different ways. Some are even 3D periodic tables with additional information being placed on a like Y sort of axis that like comes out of your screen. It's nuts. Like, I would super suggest checking out some of these more like modern niche periodic tables. All right, but the most basic, bare bones, white bread version of our current periodic table is organized in groups, which are these columns listed here, and periods, or rows, which run horizontally. The reason why the columns are known as groups is because these are the elements that can be grouped together that have very similar properties. The periods are the horizontal rows because as you work your way from left to right, you eventually have to wrap your way around the periodic table, and you end up running into a similar set of properties that occur periodically. The periodic table is also organized with the metals coincidentally on the left-hand side of the periodic table, and the non-metals are on the right-hand side of the periodic table. Now, the divide between the metals and the non-metals is not an even split, right? It doesn't get drawn right in the middle of the periodic table. In fact, the divide between the metals and the non-metals is what we can see over here, illustrated in blue and labeled as the metalloids. These elements here, boron, silicon, germanium, arsenic, antimony, tellurium, polonium, these are all elements that, all depending on the environment, have some metallic character and they have some non-metallic character. What those properties look like we're going to define a little bit later, but suffice to say that these metalloids are kind of on the in-between. So if we draw the divide like so down the periodic table, everything that is in the box I am drawing right now is considered a metal. Everything that is in this upper right-hand corner is non-metal. So the great majority of the periodic table is comprised of elements that have more metallic behavior than non-metallic behavior. So let's talk about these groups. Let's talk about the columns of the periodic table and the elements that can be found within them. Again, these are groups of elements, right? Collections of elements that have very similar properties. And we're actually going to be talking about the groups sort of as they're colored here. So we're going to work our way from the left to right. We're going to talk about this red group, then the orange group, the yellow and the brown, etc. So what causes these unique characters and properties, the reactivity of matter? Well, actually, from what we've been able to find, this follows exactly from our previous lecture. The periodic properties of matter, specifically the group trends that we are about to talk about, like reactivity, actually occur due to the electron configuration of the element. And not only that, but the intensity of the reactivity, the intensity of the trend, is going to depend on your orbital shell N. So how large in energy, what's the energy magnitude, how reactive is your atom going to be? For instance, a particular characteristic of both lithium and potassium, which can be found in the same column of the periodic table. So if we go back to our periodic table slide, both lithium and potassium can be seen in this same first group. And one of the unique properties of this first group is that they're both fairly reactive with water. If you put both lithium and potassium in water, they're going to start a chemical reaction spontaneously. Now in the lithium's case, which we can see here on the left, like if you look closely, you can see there's a little bit of, actually that's hard to read. You can see a little bit of, how am I doing this? You can see a little bit of fizzing. There we go. Now you can see my handwriting real well. Contrast. You can see a little bit of fizzing. It even looks like there's a little like bubble forming right here. What this is hydrogen gas that's being given off. But overall, aside from the chunk of lithium kind of fizzing around the top of the surface of water, you're not going to see a whole lot more. Contrast this with potassium, which yes, also reacts with water, but because the valence electrons, this 4s electron, is in a higher N, it's going to react with water with way more vigor. We can see that the person who added the chunk of potassium to water did so with tongs. Really smart, because as soon as the potassium hits the surface of water, it starts burning with this beautiful lavender, purplish, magenta-ish colored flame. It is incredibly reactive, and just by judging by the size of the flame, the chunk of lithium that is in this vessel is going to be around the same size as the chunk of lithium that is inside the vessel on the left. So we can see that there is a notable reactive difference between lithium and potassium. We can conclude that both of these atoms react with water because they both have one valence electron. We can also conclude that the potassium is more reactive than the lithium with water because its one valence electron is in a higher orbital shell. Because it is in a higher orbital shell, it's going to have a higher energy, it's going to be less stable, and as a result is going to be more reactive. So this is how we can explain or make sense of all of the group trends that we're going to be talking about. Each of these group trends is unique to the group because each of the elements in the group have the same number of valence electrons. So if we were to write out the electron configurations for each of these elements, we would find the same number of valence. That's what we're going to be looking for here, valence electrons. All right, so the way that we're going to break this down, we're going to talk about the metallic groups first, their names, some of their characteristic properties, and then we're going to be talking about the non-metallic elements. So the metallic groups do comprise, again, a majority of the periodic table, and so we're going to break down each of these by column or collection. So the metallic group names, we can see the 4 collections listed here. The first is known as the alkali metals. Now, the alkali metals occupy group 1/group 1A of the periodic table. So this is going to be the column that contains both lithium and potassium, as well as a couple of others. And as was previously demonstrated, the most signature reactive characteristic of these elements is that they vigorously react with water. Either they readily undergo a spontaneous reaction as small as lithium, or they will combust, like starting a fire, literally because the reaction is occurring so vigorously, like potassium. One of the products of this vigorous chemical reaction with water is actually a basic solution. So that's pretty cool. Group 2A. So on the periodic table, we have moved one column to the right. These we call the alkaline metals or the alkaline earth metals. Both of the names can be used. So the earth may be present, it may be not present. The reason why they are known as the alkaline metals is that when in the presence of water, they also react, but they don't necessarily react with the same vigor, let's say, as potassium does. Instead, they react and create a fairly basic solution. And yes, the alkali metals, I did say, also make a basic solution, but the alkaline earth metals actually make a greater basic solution. And the reason why is that each of the alkaline earth metals all have 2 valence electrons, which I will shorthand at times valence electron with a V, E with a superscript of the minus. So V for valence, and this is the symbol for electron. So because the alkaline earth metals all have 2 valence electrons, what this means is that provided that they actually are going to be soluble, they're going to dissolve in water, they actually have twice the reactive power. So we can get potentially twice the basicity. The transition metals are not one column on the periodic table. So we're going to go back to our periodic table. The transition metals are all of these yellow elements here. Just put a box around them. Each of these individual columns in the D block, so yes, the transition metals label is synonymous with D block. Each of the columns in this block do have some periodic or group property to them. The problem that we are currently going to be facing is that we don't have the technical understanding at the general chemistry level to really parse out these differences. In other words, we leave it to more of an upper divisional class like inorganic chemistry or physical chemistry, sometimes even organic chemistry, to really like flesh out those details. In the meantime, we're just going to lump all of these together, all of these yellow elements together, and we are going to refer to them all as the transition metals. All right, the transition metals are most notably known for their beautiful colors. The metals themselves in their pure form don't really have any color. They're all just kind of silver and, you know, metal. But when you burn them, when you put them in things like gemstones, when you dissolve them in water, you get fantastically colorful flames, gems, solutions, more so than any other elements on the periodic table. The transition metals are very signature for being able to like produce colors in the visible spectrum. We can see that partially in the flame tests that are kind of showing up here in this picture on the right. Some of the elements are the either alkali metals like lithium and potassium, we can see right here, with a signature red flame for lithium and that like lilac, lavender kind of color for potassium. Barium, sodium, and calcium are all alkaline earth metals. Copper is listed here though. And copper, much like the rest of the transition metals, all burn in beautiful colors. The metals in general tend to burn with like really beautiful colors, but it is the transition metals specifically that can lead to some really beautiful gemstone colors. Again, very beautiful colors in solution. All right, the last of the metallic groups we're going to talk about are the lanthanides and the actinides. So just to go back again, the lanthanides and actinides are the F block elements. For much the same reason as stated with the transition metals, we're not going to break them down into individual columns. We're just going to talk about them as one big group because the technicalities of their individual smaller groups are beyond the scope of this class. All right, so the lanthanides and actinides are most notably known for their radioactivity. These are all, for the most part, elements that can or do spontaneously break down and release energy in the form of alpha rays, beta rays, gamma rays, as we were discussing radioactive elements do back in chapter 2. All right, so those are the metallic groups. Let's talk about the non-metallic groups. Before really talking about the non-metallic groups, we can see here there is kind of a disclaimer that period 2 elements, so those that are in row 2, have either forms like they're physically constructed or they have reactivity that is pretty distinct from period 3 or more. In other words, the elements of boron, carbon, nitrogen, oxygen, and fluorine are relatively unique compared to the remainder of the P block underneath them. So it can be hard to draw any conclusions about like some group trends if these particular elements don't really behave in line with the rest of their group. To get a better reason for why this is, let's just turn back to our periodic table again. All right, if we observe the periodic table, we can see our boron, carbon, nitrogen, oxygen, fluorine are right here. And the reason why we kind of set these apart from the rest of the group underneath them, particularly the boron, the carbon, the nitrogen, and the oxygen, is because the metalloids, again, are cutting these groups right in half. So boron, as a metalloid, is going to behave very differently than aluminum all the way down, which are going to be characteristically more metallic. Carbon is going to behave very differently than silicon and germanium, which are metalloids. And then there's tin and lead underneath, which are super different than carbon, right? These are both metals used either in tin cans or lead piping. Nitrogen and phosphorus are both going to kind of have similar properties, but then you get into arsenic and antimony and then bismuth underneath, and they're all super different. So it can be hard to draw any really good group characteristics about any of the groups from like, we can see 13 here all the way to 16 especially, because they're just cut in half. So the top half is going to have a unique set of characteristics, the bottom half is going to have a unique set of characteristics, and for that reason we don't really have, particularly with groups 3A/13, 4A/14, they don't really have any group names as a result. Despite the fact that we don't really have a good name, right? There's not a team name for group 13 or group 14, 3A, 4A, however they're labeled on your periodic table, there is still some commonality between the two. So for example, if we turn our attention to two elements in the 4A/14 group, carbon and lead, we can get a pretty good, or can lay out a pretty good example for how these elements sometimes can be considered to be very different, but sometimes can be considered to be very similar. In the former set of descriptions, we can observe carbon in either its coal form or its diamond form, and see pretty distinctly that it is not the same as lead. Right, coal, diamond, both of these solids being formed by carbon are very brittle, like you can dust off or crumble coal in your hands. You can smash a diamond with a hammer. They're not moldable like how lead is. Right, lead is a very distinct metal. We can see that there is a bit of luster to this open face right here, so you can cut it without really like shattering it. You can form lead into a whole bunch of different shapes, which is why it was used for plumbing for so long. It's actually pretty easy to work with. So in terms of physical description, these things are very different. They're not, they're both solids, and that's really the only similarity they have. Carbon does not conduct electricity, lead does, etc. So we have a pretty distinct line here in the sand between carbon and lead. Despite that fact, carbon has a total of 4 valence electrons. Similarly, lead has a total of 4 valence electrons, if we are assuming that we are just looking at the s and p suborbitals. Because yes, technically lead also has some d pseudovalence electrons, but we're just ignoring those for now. When it comes to the valence behavior, both of these elements has 4 valence electrons. And because both have 4 valence electrons, chemically they can behave in the same way sometimes. For instance, your body is made up of a lot of carbon. We are carbon-based life forms. Carbon is able to be processed and recognized by the human body pretty easily. And a part of the mechanism that is required for your body to be able to look at carbon and see carbon and understand carbon are these 4 valence electrons. Right, an element of carbon to another element will appear to be comprised of 4 valence electrons that are ready for reaction. These are the things that are on the outside, the electrons on the outside that are ready to react. Lead to your body appears very similarly. It has 4 valence electrons also. And even though the reactivity of lead, like how reactive it is, the magnitude of reactivity is going to be different than carbon, to your body, it still just sees 4 valence electrons. And this is what leads to a lot of problems, such as lead poisoning. And again, I'm giving kind of a hand-wavy description here. I'm not going into a lot of detail on the specifics of the mechanism, so take this with a grain of salt. But your body can't tell the difference very well between carbon and lead. Because your body can't tell the difference between the two, if you ingest lead, let's say in the form of like lead paint chips, which used to be a thing, like lead actually tastes kind of sweet. That's why kids used to eat lead-based paint chips when it was peeling off of houses. So if you ingest lead and your body sees it and responds to it as it does to carbon, your body is going to be shuttling this lead into places it shouldn't be. Places like your cardiovascular system, your nervous system, and because again your body doesn't recognize that it's not carbon, won't process it and filter it out the way that it should for the most part. I mean, there is going to be lead that gets filtered out, but not all of the lead will, and it's the lead that sticks around that causes the problems. So despite the fact, again, turning to the top, that group 4A/14 doesn't really have a cohesive group name, there are going to be instances where the two are going to be confused by the environment, like for example, your body, and they will be treated the same. They're going to have they will have similar enough reactivity where we can very clearly tell that they are in the same group of the periodic table. All right, I'm going to blow by the other two since in the same vein as carbon and lead with the groups, just talked about, 5A/15, 6A/16, there are enough elements in each of these groups that they have been given a name. 5A/15 is known as the pnictogens, but really this refers, or this name is in reference to nitrogen and phosphorus, not necessarily the rest of the group. Similarly, the name chalcogen refers to oxygen, sulfur, and selenium, but doesn't really reference the rest of the group. So we're really talking about the elements that have similar enough properties that warrant giving the group a name. All right, the last two groups on the periodic table that we are going to talk about are the halogens and the noble gases. The halogens all have 7 valence electrons. The noble gases all have 8 valence electrons. And I just realized, hold up, let's go backwards. Pause. The pnictogens, I can't believe I forgot to write this down. The pnictogens all have 5 valence electrons. The chalcogens all have 6 valence electrons. I'd mentioned with carbon and lead, the group 4A/14 have 4 valence electrons. Group 3A/13 has 3 valence electrons. And we can write out each of the elements' electron configurations to really confirm this if you would like. Go right ahead, get some really good practice in. But it is the number of valence electrons that are present that are going to, again, ensure the similarity in certain chemical properties of these elements. So returning to the halogens with their 7 valence electrons and the noble gases with their 8 valence electrons, I apologize again for completely neglecting to include any of the previous valence counts until I realized that I had missed them. Our halogens with their 7 valence electrons, their notable periodic property, their group trend, is that they're smelly. I know it's a strange characteristic, but if I remember correctly, and editing, Dr. Billman, please double check this for me. If I'm remembering correctly, halogen in Greek roughly translates to odorous. They have a very notable smell. If I'm incorrect about that fact, that will be on the screen. If I'm correct about the fact, the confirmation will be on the screen. I hope I'm right. I hope I remember that correctly. All right, so the halogens, most notable for their smell. And they're not smelly in like a putrid way. They're not smelly in like a disgusting kind of garbage way. When I say smelly, I just mean that they have a very distinct odor. For instance, if you've ever been to a chlorinated pool, you're gonna know what that smell is. It's a very like sharp, almost like corrosive smell in your nose. It's very, very pervasive. It lingers. But that's the smell we're talking about, the chlorine pool kind of smell. Fluorine has the same smell. Bromine has a very similar version of the smell, it's just more exaggerated. And iodine is even more corrosive than that. So the elements are all very volatile. We can see that fluorine and chlorine themselves are actually gases. Bromine, in this vial we can see here, exists as a liquid. And iodine exists as a solid. But despite that fact, there is a lot of the bromine that has evaporated up into this tube. That's what's causing this like orange haze. And with the iodine, we can see that there's like this purple kind of haze coming off of the solid. Again, it's very volatile. And it is this volatility that leads to the odor that is unique to the halogens being able to like pervade a particular area. You can smell them from a pretty good ways away. All right, last but not least, the noble gases with their 8 valence electrons. These are elements, as a result of having 8 valence electrons, we have found are chemically inert. They do not react with other things. Turns out that having 8 valence electrons is incredibly stable. 8 valence electrons, as it turns out, is what each of the elements strives to have, and we're going to talk about the implications of that more in Chapter 5 as we start forming molecules from these atoms. But because the noble gases are already energetically satisfied, smiley face, they don't really have to react with anything. They are perfectly content being off on their own. This is actually where the name noble gas comes from. They were named in reference to the nobility of the days of yore that tended to not interact with the working classes or lower class folks. Because chemists back in the 1600s, 1700s, 1800s were really blue-collar workers. They were getting dirty in the lab, they worked with their hands. They referred to this new class of element as the noble gases were being discovered in reference to the noble class, which tended to see itself as being superior and not needing to interact with the lower chemists. So it was really named as kind of like a fun jab in reference to these like upper classes that saw themselves as being too good to interact with anyone else. It's kind of a fun fact. All right. This is though where we are going to conclude our lecture. There are no section review problems corresponding to what we have talked about today. So really from here, there's no real practice work. It's just catch up on your reading. Make sure you peruse the sections that were listed at the beginning of the slide. There's some information pulled from Chapter 2, a couple of different sections of Chapter 4, since Chapter 4 is organized in a very strange way. I apologize for that. I have no control over it, and I wish I did. But without further ado, if you have any homework, do your homework, and until next time, class is dismissed.